The objective of this chapter is to find the electric field using Gauss's law. Gauss's law is the electric flux through enclosed surface is proportional to the charge inside this enclosed surface. So we also use the integral on enclosed surface EdA. E is the electric field inside this enclosed surface. Okay, let's do an example. Let's choose plus Q is positive charge. We want to find an electric field E at certain distance from that charge. So the symmetry of our point of charge, spherical symmetry, is point of charge. We consider that sphere. So our Gaussian surface also it will be spherical. This is how we choose the Gaussian surface. You take the symmetry of the charges you have. So to find the electric field. Now then we go use Gauss's law. What says? The electric flux is given by the integral on enclosed area EdA and is proportional to the enclosed charge. So this is the definition of electric flux. This term, this scalar, we have E times dA. Here we just E times dA times cosine of theta. Now I need to know what is theta. I need to know what is theta, what is dA, and what is E. So E is very simple. Last time we talked about electric field direction when we have point of charge. If the charge is positive, we just pass the line from the charge and the point, and the electric field will be outward. So if the charge is negative, it will be inward, means toward the charge. So the direction of our electric field in this case is just the line that passes, and then direction is outward. Now I need to find this vector dA. The vector dA is what? If I take this element of area, this is the element of area, what we call dA, because around this point M, you choose an area dA. This area, let's choose different color. This area dA, by definition, is the element of area times the normal to this area. The normal to the area is the perpendicular to the area A and outward. In this case, if this is my area, this means dA, or the same thing is I have this area dA times the vector normal vector, which is vector that is perpendicular to the area, and unit vector perpendicular to the area. So this is how we get the area in terms of vector. You take the element of area of vector is the area times the normal vector unit, which is perpendicular to that area and outward by definition. This is my vector dA, also is outward in the same direction as electric field, means the theta, in this case the theta is 0, cosine of 0 is 1. Our electric field, this will be just E dA, because cosine of theta, cosine of 0 is 1. Our electric flux, here we just the integral AdA, take this off, AdA, we said electric flux equals to the integral AdA, which is a Q enclosed over epsilon 0. Now our electric field from any point here is uniform, because we have 1 point charge from any distance, the magnitude is the same. That means electric field is uniform. We can get it out from the integral. It will be just the integral of this area, this element of area. If I add all these areas that I have all around, it will be just the spherical area. the sum of all this element of area of that sphere will be the total area of the sphere, and the total area of the sphere will be 4 pi r squared, and it is equal plus q over epsilon 0. So our electric field will be just plus q over 4 pi epsilon 0 times r squared. Now let's find electric flux at the area 1. This one we call it area 1, and this area we call it area 2. First thing you need to look at to find the electric flux, look if there is a charges. Remember, the electric flux equals to the q enclosed over epsilon 0. So for the area 1, do I have a charge? Yes. Electric flux on the area 1 equals just to plus q over epsilon 0. For the area 2, you look inside, you don't have anything. Your electric flux in the area 2 is 0. So the electric flux is proportional to the charge. So if there is no charge, there is no electric flux. Let's say we have this conducting wire full of charge and the density is uniform. And it's charged with positive charges. Okay, so the density is lambda is constant. Charge is uniform. So if the charge is uniform, means that lambda is constant. The objective is to find an electric field from distance r from the wire. And we suppose this wire is infinite. What we mean in reality infinite wire is when this distance from where we calculate the electric field is too small compared to the length of the wire. This is what we mean by infinite wire in reality. So let's use Gauss's law to find the electric field at this distance r. Now the Gauss's law says the integral on enclosed area EDA equals Q enclosed over epsilon 0. This is the electric flux using Gauss's law on enclosed area. Now let's consider the enclosed area. I take this point and I make a cylindrical surface. So if I have wire, I choose surface cylindrical. We said last time if we have point, we choose sphere because the charge has a format of sphere. Now this wire we consider has format of cylinder, and we choose cylindrical format for Gaussian surface. Now what I see here, let's clean this. What I see here, I have this cylinder, Gaussian surface, cylindrical surface. Now, how many areas I have? I have this lateral area, the base, I call it base 1, and I call this one base 2. So I have the total flux in this area. It will be the flux from lateral plus the flux from the base 1 plus the flux from the base 2. So to find if the flux is 0 or not, you just look to the direction of your electric field and the normal to the surface of the area. So if the normal to the surface of the area is perpendicular to your electric field, means there is no flux. Now let's look for the base 1 and 2. For the base 1, this area, base 1, so the normal to this base 1 will be like that, downward, I call it N1. But what would be my electric field that produced by all these charges? It will be perpendicular, it will be in that direction, and it will be all the time perpendicular to this base. So what that tells us, the flux is 0 from the base 1. The same thing for the base 2. The electric field produced by all these charges on this line will be in that direction, or outward, but all the time you'll be perpendicular to this vector n2. So what do you see? What do you see if it's perpendicular to the area B2? That means this flux is 0. This one also is 0. So the only flux I have is lateral flux. Why? Because the electric field will be all the time. If I take this area here, and the electric field will be in that direction, and lateral area dA will be collinear and in the same direction. So the electric flux total will be just the integral of E dA and the dA lateral. So in this case, it will be just the integral E dA. So remember, this electric field will be uniform because it will be equidistant from the line, and the distribution is uniform because we said lambda is constant. Electric field also will be constant, and we can get this outside from the integral. Remember, this will be just Q enclosed over epsilon 0. Then the electric field outside here, because it's uniform and constant, will be the integral just on the lateral area. So we said the electric flux is integral on enclosed area E dA, and all we have was lateral area. We said what is the lateral area? This is our cylinder. Lateral area is the area that has this length. Remember, it was just dl. If I go from the whole wire, the lateral area, it will be all the whole length, it will be L times the circumference. So the total lateral area of this Gaussian surface, it will be what? It will be the circumference times the length of the wire, or the length of the cylinder, the Gaussian cylinder. It will be 2 pi RL is the length of the whole wire times the circumference. This is the total Gaussian area is the total lateral area that includes the whole wire. It will be the total length of the wire times the circumference. This cylinder is just element of cylinder, which is dl times the 2 pi r. But we need the whole length of the cylinder, the whole length of the wire. So now we go here. The Q enclosed. What do we mean by Q enclosed? Is the charge inside this Gaussian cylinder. The total charge inside this Gaussian cylinder, we just said, is Q. And remember last time what we said about when we have uniform density, charge density, Q will be just the total length times the density. We said Q equals to lambda times L. The charge is uniform. That means the density is constant. We just multiply lambda times the length to give us the total charge for this wire. Now divide by epsilon 0. What do we see here? The length vanishes. Our electric field become just lambda over 2 pi r epsilon 0.